Hello everyone, welcome back to another video. This one will be a short one. We're going to be looking at the Doppler effect. As always, if you'd like to give it a go, please pause the video and I'll do the answers in 3, 2, 1. Question 1.6. The spectrum of helium emitted from a star moving away from Earth is compared to the spectrum of helium found on Earth. Which one of the following statements is correct? Let me explain this using a diagram. So, suppose you have a person standing on Earth and they are detecting, using some instrument, helium that is moving away from Earth. Let's draw helium as that shape. Now, if it's moving away from Earth, right, this helium is going to be emitting radiation. Whatever radiation is being detected, that's the radiation that it's emitting. Now, that radiation is going to be emitted in all directions. We're just going to be focusing on the left and right side. Now, what happens is, as this helium moves to the right, it's going to squash or compress the wavelengths of EM radiation that it's encountering as it's moving forward. So here you're going to find a region of low wavelength. So in front of it. And that means leaving behind, it's actually going to be stretching the wavelengths of radiation that is behind it. So you'll find that the radiation that's behind it is actually going to be stretched further apart. So this is going to be higher wavelength. So the person that's detecting it is going to be detecting a higher radiation, a higher wavelength or longer wavelength. So the options that we have is A and D. Okay, now remember, radiation, EM radiation, is governed by this formula. C, or the speed of it, is equal to C equals F times lambda. C is a constant, meaning that if the wavelength is increased, the frequency is decreased. So the correct answer here is going to be A. Low frequency, long wavelength. All right, so let's move on. Question number 6. A stationary listener records the frequency of the sound emitted by a siren of a police car when the car is traveling at a constant velocity of 26 meters per second, approaches the listener. So this is important. Approaches the listener, the recorded frequency is 615. When it passes the listener and moves away, the frequency is 526. State Doppler. That's fine, you have the definitions. 6.2, use the information given to calculate the speed of sound in air. This is 5 marks. So 5 marks either is going to be simultaneous or 2 equations. In this case, let's write out our equation and we can figure out which one it's going to be. So our equation for Doppler is FL equals V plus minus VL over V plus minus Vs multiplied by Fs. In this case, we don't know the frequency of the source and we don't know the velocity or the speed of sound in air. That means we're going to use simultaneous. So we need 2 equations. And the 2 equations we can get them from setting up an equation when the police car is approaching and when the police car is moving away. Okay, so when it's approaching, we're going to say FL equals V. Now when it's approaching, just remember the following. It's going to have a big top and a small bottom. So V plus VL divided by V minus Vs times fs. Let's substitute the values we know. When it's approaching, the frequency is 615 equals v plus 0, the listener is stationary, divided by v minus 26 multiplied by fs. And when it's moving away, remember the following: small top, big bottom. So the equation is going to be FL equals V minus VL divided by V plus VS multiplied by FS. So FL, when it's moving away, is 526 equals V minus 0 divided by V plus 26 multiplied by Fs. That's equation 1, that's equation 2. Now, we can join them, we can solve in terms of Fs. We can say that 615 open bracket V minus 26 divided by V is equal to, because remember Fs is the same for both, that's going to equal to 526 open bracket V plus 26 divided by V. Now the V's can cancel, you're going to get V equals 333,33 meters per second. So that's the answer here for 6.2. 333,33 meters per second. Question 6.3. Calculate the wavelength of the sound emitted by the police siren. So we can work out Fs. From the equations here, we can say that Fs is equal to 615 into 333.33 minus 26 divided by 333,33, and put that in the calculator and you get the frequency of the source is 567,03 hertz. So if they want the wavelength, we can then say that what equation? I think we can use V equals F times lambda. We know the frequency 567,03 multiplied by lambda, and the speed of sound we worked out as 333,33. We can solve for lambda. Lambda is going to be 0,59 meters. Okay, and the last question, 6.4. Sketch the graph of recorded frequency versus time for the motion of the car as it moves towards the listener, past the listener, and moves away. Label T1 on the graph. So this one's quite straightforward. 6.4, if you have your graph, you'll have time, you'll have frequency, remember in hertz, and that will be in seconds, I'm assuming. Yeah. So at the start, when it was approaching the listener, the frequency was 615. And then when it moved away from the listener, it was 526. And this change happened after T1. So it was this, then it changed to that. And that's our graph. Actually, it dropped here, so we need to join that. And that's our graph, that's our answer. So if you found this useful, please consider leaving a like, subscribing, sharing. If there's something you'd like me to do specifically, let me know in the comment section below. Until the next one, bye-bye.